Hello and welcome back to Beginning C++. This week we're going to be talking about functions. Functions are a fundamental concept in computer science. They defined, honestly, a new paradigm of programming for most programming languages. Functions are a way of giving a name to a set of instructions, right? A procedure. In the same way that variables are sort of a way of giving a name to a piece of data. Once we define a procedure with all of its steps and all of its individual lines of instructions, by giving it a name, it makes it easier to sort of invoke those steps. I can just say, oh yeah, I want to do this larger thing, which I know comprises, 15 smaller things that need to be done, but instead of having to constantly go back to those 15 smaller things, I can just use the name and then have you do that whole thing. Chances are if your parents tell you that you have to clean your room when you were a teenager, right? You would know all the steps needed to do that. They didn't have to tell you that you needed to put your laundry in the hamper and you needed to make your bed and you needed to pick up, that was assumed in the go clean your room, right? That's what we're doing. We're giving a name to a set of instructions. So you've been using functions this whole time. This is a function. It's a very famous one called main. Main is important because it's the first function that gets called when your program gets run. But it has all the same parts that we're going to talk about in our functions. There's a couple things that are missing because you don't need like a declaration and stuff. We'll get to that later. But point being, you're going to notice a lot of these similarities to the syntax you're already using. So let's start with the higher end, right? Let's think of functions sort of in a larger scope, like, a more higher level way of thinking about them. And I think that you can think of functions in three ways. You can probably think about them in more than three ways, but you can at least think about them in these three ways. The first is that functions are subroutines, right? They are literally, as I described them, a list of instructions that have been given a name that when you say, hey, do this procedure, everything inside of that list will be done, right? All of those sub-steps. To me, this reminds me a lot of French cooking. Now, granted, I do a lot of cooking, but bear with me here. French cooking is amazing because everything is sort of hierarchical, right? There are 5 mother sauces. Based on those 5 mother sauces, you can create a whole bunch of other sauces, and those sauces can be used in lots of different recipes. But in French cookbooks, they're not going to waste time telling you those same steps over and over and over again for every single recipe, right? So you might have, in the front of the book, something like make bechamel. Bechamel is one of the 5 mother sauces, right? And you've got steps. You have to heat a pan, melt some butter, add some flour, cook for a couple minutes to get rid of the raw floury taste, then add milk slowly while whisking, and then cook for another 5 minutes until thickened. Bam, bechamel. It's a simple milk sauce, I guess, right? From it, though, you can make all sorts of other stuff. So you might see another recipe later on that talks about Mornay sauce. Mornay sauce starts with step 1, make bechamel. Now, if you think about these as functions in a computer, what I'm really saying is there is a function called make Mornay sauce. It's my recipe. The first step of make Mornay sauce is make bechamel. So I'm going to leave that recipe at that point. I'm going to go to the make bechamel recipe, and I'm going to do all 6 steps under the make bechamel recipe. Once I'm done with making bechamel, I can exit that, go back up to the make Mornay sauce recipe, and start at step 2, adding Gruyere and Parmesan, stirring until the cheese is melted. You've got cheese sauce. I mean, it's called Mornay in French, but it's cheese sauce, right? That's sort of the way it would work, right? And you could imagine that there's another recipe. Make mac and cheese, right? What are the steps to make mac and cheese? Make mac and cheese. Step 1, boil water. Step 2, add pasta to water. Step 3, make Mornay sauce. Exit, go to make Mornay sauce. Making Mornay sauce. First step, make bechamel. Exit, go to make bechamel. Finish all 6 steps. When I'm done, go back up to step 2 of make Mornay sauce. Add Gruyere and Parmesan. Stir cheese until melted. Go back to make mac and cheese. Drain pasta, right? I'm sort of creating these steps in a hierarchical pattern so that I can do stuff a little bit more easily, right? I don't have to reinvent the wheel just to make mac and cheese. I can say, boil pasta, make Mornay sauce, combine the 2. Just makes it a little bit easier. And maybe the analogy is not working for you, but we'll see. Another one that this is very popular in math classes is to view functions as a machine, right? So the thing that you don't really get with the whole idea of a subroutine is that Functions act like functions, right? Like that mathematically. They can take input and they can provide output. So you can put things into the function and get out a result. And so sometimes people will visualize this in math class as a little function machine. I can put arguments into the function. The function does some work. In fact, it might even do some work that has some side effects. It does other things. Print stuff to the screen, I don't know, send stuff across the network, whatever. But then at the end, it outputs a value, right? That's another way of thinking of a function. It does something. It does some work to something. You can define it as sort of like a procedure. Oh yeah, I'm going to, put this into our, letter opening machine. So I take a sealed letter, I put it into a letter opening machine, and it comes out an unsealed letter. It's a function machine. What's the function do? It opens envelopes, right? What does your function do? Whatever you want it to do, right? And so that's the idea. Functions can take input and produce output. And I said this was often used in math classes, which is really my third way of thinking about it. Functions as math. When you eventually get to this point of algebra, you start seeing the f of x, this is meant for you as the computer programmer, right? This is where we start talking about functions. And what we're really doing is we're defining what these functions do. So the f of x is equal to x squared. What does that really mean? It means that we've defined a procedure called f. And when you do that procedure on a value, you're going to square it. So what does it mean to something? Let's switch over to the g. What does it mean to g something? In this case, you double it, right? What does it mean to g something? It's a procedure where you double something, right? That's how that works. So the procedure f is to square, the procedure g is to double. Now, you can do the thing that they probably taught you to do in algebra class where it's like you have to substitute things in. So, what's the f of 3? Well, the f of 3 would be I have to put the 3 in for the x, and then I have to substitute it over. So there's 3 squared, and 3 squared is 9, so the f of 3 is 9. But, if you're a little bit better with math, you don't actually need to substitute anything. You can just think of it as a procedure. What does it mean to h something? Oh, that's when you double it and you add 3. Okay, so the h of x is 2x plus 3. Regardless, you can then do this sort of nice thing where you can sort of nest them together, right? So here at the bottom, I've got the f of the g of the g of the f of 2, right? So I take that 2 and I apply the f function to it, right? I do the f procedure to it. And you can almost picture that f of 2 kind of going poof, right? And it's being replaced with a 4, which in this case would have been the same whether you had done the g or the f, but that's just for the input of 2. And so 2 squared, poof, it becomes a 4. And then I've got the g of 4, right? Now on paper you would scratch it out and write the 4, but this is video, I prefer to go poof, right? So the poof, you get the 4. Then you have to g the 4. Well, what does it mean to g of 4? That's just doubling it. So poof, 8. Then I have to g the 8, because we're working our way out. What does it mean to g something? It's just doubling it again. Okay, poof, 16. Then I have to f the final thing, right? So how do I do that? Well, you just poof, get 256. I'm pretty sure that's the answer. Regardless, you get whatever 16 squared is, which I'm 99% sure is 256. I'm usually pretty good with powers of 2 because, the whole computer science degree thing. Regardless, functions as math, they're connected. They're literally connected. This is where we get our idea of functions from. By the way, I'm more of an engineering type rather than a math type, and so I have one slight issue with this. Those names for functions are terrible, right? As an engineering person, I would want my names for functions to be far more descriptive and actually tell me what the function does. Also, it would keep me from having to say effing things, and then, you juvenile students are going to make fun. But still, they should have called it the square and the double. See, now that makes perfect sense to me. The square of the double, the square of 2. I mean, just choose better names. As a computer programmer, do it this way. Don't do it the other way. Also, get rid of x. That's not very descriptive either. All right. So now, we're actually to the point of how do we actually create and use functions. We have to do 3 things. We have to declare the function. Technically speaking, you don't have to, but we're going to do it right from the beginning because later on, when we want to actually create code that looks like industry code, where we have separate header and implementation files, I want to be able to, if we just start the process now, it's going to be so much easier to create header files later. So, declare your functions. Then we're going to implement the function, actually create the steps that we need to do when you call that function. And then lastly, to use it, we just have to call the function. You can call it as many times as you want. So let's start with the declaration. The whole point of a function declaration is just to tell the compiler, hey, I'm going to have a function by this name. It's going to take these parameters, it's going to have these parameters, right? It's going to take these things as inputs, at least the types. You don't even need names at this point. You just need at least the types. And it's going to return this type. What that allows the compiler to do is, as it's going through your code, parsing things, it can find lots of little errors that might pop up. Where, you know what, this function takes a string and you sent it a double. And that's not going to work because I can't convert a double to a string automatically. So it'll throw up a little compile time error. That's great. That helps you out. You can see, oh, that's right. I thought I was using the other function here. Let me fix that. Maybe you grab a function, but you kind of forgot what it returned and you used the return value in the wrong way. Okay, well, it's going to tell you, right? It's just allowing the compiler to check for errors. And so just by declaring it, we just have to give what's it going to return, what's its name, and what does it take. So here is the generic syntax on the top and some concrete examples in C++ at the bottom. You have to have the return type, the function name, and the parameter type. There's another little optional thing you can put in there, which I sometimes do, but that's just because I'm a little bit lazy, and I'll talk to you about that in a second. But for right now, this is the minimum that you need. So, return type, let's say I'm doing the area of a line. Lines don't have area, so there's no parameter type. And it returns a float. In fact, it could probably return an integer. It would be 0, right? But still, area of a line takes nothing. Area of a circle only takes one float. Why? Because circles have radiuses, and I can get the area from that. So this will take a float and return a float. Area of a rectangle takes 2 floats. I need length and width, and that'll return a float. So here are my generic sort of little syntaxes. Now notice if you do not have a parameter type, or so you don't have a parameter at all for your function, like area of a line, which is a bit of a ridiculous example of a function, you still have to put the parentheses there. Without the parentheses, your compiler will not see that as a function. So parentheses are always there no matter what. If you don't need a parameter, just leave them blank, or leave what's inside blank. Then we need to implement our function. At this point, we need to actually talk about solving problems, because the writing of code is usually not the hard part. The hard part is designing something and actually solving problems. If I haven't said it yet in this class, I will probably say it many times. Your job as a computer programmer is not what you do on the keyboard, it's what you do on the whiteboard. You are solving problems. You just happen to be using a computer in order to do that. So, what do we want this function to do? What data do I need in order to do that? What do I want it to return? What do I want it to return? And what do I want to name it? Which sounds like a silly thing, but badly named functions can sometimes cause problems, especially if you don't actually understand the problem very well and you end up thinking you did something but you didn't, and you write a function saying it did something. Point being, just give things good names. So here is at the top the generic syntax for a function implementation. You're going to notice that first part looks really, really similar, which is why we'll get into a second why I sometimes flub things a bit. But it looks very, very similar. Then we have some curly braces and a whole bunch of stuff inside. We're going to use as our concrete example our square function that we talked about. So this is just going to take a number and it's going to square it. Simple. So let's start with the first thing, the return type. What are we going to return? Now I could do integer. Technically, if I send any integer to, a square, you square any integer, you're going to get another integer, right? So I could have it take an integer and return an integer. But that means I could never send 1.5 or 2.75 or anything that had a decimal point. So what I could do is have it take a double. But if I have it take a double, then what it returns is not going to be an integer. That means that if I want this to be a bit more flexible, I'm going to have it return a double. Remember that a double is just a floating point type number, the kind of the decimal point, but it takes twice as much space, twice as much memory, which in this case is a good thing because floats can sometimes have rounding errors. This minimizes that. So return type, double. this function, when it goes poof, what it's going to leave behind is a double floating point type value. Then we have to give it a name. It's going to square things. I'm going to call it square. It's a simple name, but I think it's sufficient. All right, next, parameter type and parameter name. So inside those parentheses, I'm going to create the type double. Now, by the way, you notice double, square, double. Like we would have had to do that for the prototype, right? Like the prototype would have had that already. The only thing I need to add into it, the thing that's new from, well, sorry, I said prototype. I usually say declaration, but those two terms are synonymous. The only thing I'm adding from the declaration is the name of the parameter, and that's because this is the actual implementation. I'm actually going to use this parameter, so I have to give it a name. But the thing is, I actually could have given it a name in the declaration as well. It's not needed. The compiler doesn't care. But if you put it in there, what you can do is, later on we'll define classes, and you're going to have a bunch of like member functions that you're going to create for those classes. Or even if you're just creating a whole bunch of function, declarations. Like, here are all the functions I want to write. You can just declare them all. That means that I could, grab, highlight, copy, and then go to my implementation file later. Right now, it'll just be further down on the same page, and then paste. And now I've got all of the headers for all of my function implementations. I just need to replace the semicolon with a curly brace and start implementing. It sort of gives me an easy to-do list of the things I need to now implement, the things that I declared earlier. So I actually keep my function declarations and my function implementation headers, which is kind of the part you're seeing here, the exact same. And I put in the names anyway. It just allows me to copy and paste, create a to-do list. It's a workflow thing, but you don't have to, not needed. Here, you need to have a parameter name. So we're going to call that input number because I'm putting too many words in for whatever reason. Next, curly braces. This is new. I'm not going to end this with a semicolon like I would a declaration. Now I actually have to create a block of code, and those curly braces define the block of code. Anything inside those curly braces is inside the function. Anything outside those curly braces is outside the function. This is also going to define scope for us later on. But the idea is that, this is defining anything inside of this are going to be all the different commands that we are going to execute when you call this function. Now, as it turns out, this function only has one line of code it needs to implement. It's a special line of code that uses a keyword called return. So what return does is it's actually going to return a value. That's the poof part, right? It's going to return a value, and the value it's going to return is whatever comes right after it. So here we're going to, try to actually evaluate that expression, input number times input number, which is how you square something, and then whatever that ends up being, we're going to return it. So what is input number? Input number is a sort of like a variable, right? We call them parameters because they're a special type of variable, but they act just like variables. I created a variable called double input number. When you actually use the function and you call it, you are going to send it an argument, and that argument is going to initialize that input number. So that input number is going to be whatever you send it. Square of 3, square of 16, square of, 42. That then becomes input number. And so then I take that number, I multiply by itself, and then I return that to whoever called the function, right? That's kind of the way we implement our functions. Now, the reason we're doing the return, as opposed to maybe something we would have done earlier, right, where we just print out the value to the screen. The bottom example just prints out the value to the screen. It actually doesn't return anything. It returns void, which means nothing. If you want to return nothing, you say void. You can't just leave it blank like you can with the parentheses, because there's no way to parse that there's nothing there before you get to you have to have something before the name for it to get it right. If they had put some sort of symbols around it, then maybe that'd be okay. But regardless, the bottom one just prints out a value to the screen. Now you would think that this solves the problem, which it kind of does, but the problem is then I can only square things once, and I can't take that returned value and actually use it in larger expressions. I can't save it to a variable. I can't do anything with it. I can't pass it as an actual argument to another function. I can't because you just printed it to the screen. I can't do any work with it. So returning something actually allows me to use my function calls in bigger and larger, expressions. So returning, superior. You could do both, but the printing to the screen then ties it to that, which maybe you don't always want to print every time you square something to the screen, right? Better to just put the top, and if you want to print something to the screen, then you let the person who wants it on the screen do the cout, not you. All right. Lastly, with function implementations, the idea computers hate ambiguity, right? If you say you're going to return something, you need to return something, and it should be of the type that you said it was going to return. Otherwise, everything is going to end up with errors. If you are taking something as a parameter, or you have parameters that take arguments, and you have to send arguments that match those parameters. You have to sort of get your inputs and outputs. If you are really good at hooking up like DVRs or even DVD players to televisions, like you get like, oh yeah, this has to go from the output of this to the input of this, and then from this HDMI to you're going to be great at functions. Functions are really a lot about communicating with one another. One function communicating to another by sending arguments and receiving back return values. Lastly, we actually have to use our function, so we have to call it. Calling it simply means using the name, parentheses. This time it's not a parameter list, it's an argument list, and you're going to send actual values, arguments, to your function to get the result. So here is an example of a function call. Here I've got main double result is equal to, or I'm assigning it the value to the square of 2. So here we're going to evaluate the square of 2. It's going to go poof, and it's going to be replaced by a 4, and we're going to assign that 4 to result, which is a double. Then I can use result anywhere else in my program, and I'm perfectly fine. So here's another example where I can't just print out the value. Here I wanted to print it out with a little bit of a sentence around it. Well, if you just made square 2 print out the value, I wouldn't be able to use that. I wouldn't be able to assign it to a variable and hold on to that value for a little bit. But here I was able to do it. Now here's the thing, I can actually use that function call in multiple places. So since I clearly return 0 and end main after this line, I don't need to create a variable to hold on to a value that I'm never going to use again. I can actually just use that function call right there in the cout. Now this would be a great solution if I never had to use the value again. If I did have to use the value again, I'd probably have to consider, well, maybe it's actually better off holding it in memory so that I can use it multiple times and not have to recalculate with a new function call each time. This is kind of a design decision. You're sort of balancing clock cycles of function calls versus how much memory are you using. And there's no hard and fast rules as to which is always right. Point being, you should at least be aware that you're entering a trade-off situation here. In this case, I'm saving memory. I'm actually saving clock cycles too, but because I only have the one function call, but my situation is I'm only going to use this value once. I'm never going to need it again, so there's not really much of a trade-off I need to worry about. But anyway, this is also doable. In here, that returned value of 4 is just sent using the arrow to the cout directly. I don't need to store the value. Now you've probably noticed me correcting myself sometimes because I tend to be pedantic about it. I need to make sure I get it right for the most part. And that's the difference between arguments and parameters. I have seen some computer programming books use the term parameter for everything. What you send, what you receive, everything, it's all parameters. And, point being, you may not find pedantic people in the real world and you'll be just fine. But the difference between an argument and a parameter, when you're calling a function, you are sending arguments. Right? You don't have to specify the type, it's a value. I'm sending a value to my function. So that's an argument. So when I'm implementing my function, I'm creating parameters. Those parameters will receive the arguments, right? I'm essentially assigning a value to the parameter every time I call the function. And so parameters receive the arguments that are being sent to the function. Arguments are what you're actually sending when you make the function call. Bear with me, this may be a bit of a trigger warning for vegans, but my first job when I was 16 was as a butcher, so I kind of picture it like this. I have a machine. When I created the machine, I said, ooh, what's my parameter type? My parameter type for this machine is it will accept meat. What kind of meat? Any kind of meat. Doesn't really matter, just accepts meat. Okay, what's the return type? Well, that's usually set by this little die thing you put on the end and you have to screw on, whether you want fine grind or coarse grind. In this case, we set it to coarse grind, but it doesn't really matter. I'm going to return ground meat of some sort. This is when I'm defining my machine, right? Now, when I actually use my machine, you can't send a machine meat. Meat isn't a thing you can do, right? Meat is a category of things. I actually have to send a specific meat. I have to put in like beef shoulder. Now, if I put beef shoulder in, that would become my argument. I'm sending my argument to the parameter. The parameter is receiving it. I'm assigning that value right now. As we crank the machine, I'm going to get a specific return value for that specific argument. If you put in beef shoulder, I'm going to get ground beef. If you put in pork butt, I'm going to get ground pork. If you put in lamb shoulder, I'm going to get ground lamb, right? Whatever my arguments are determine my return value, even though my parameters and my return type never change, right? That's when I set up the function, when I'm implementing the function. This is when I'm calling the function and actually using it. I'm sending specific arguments and getting a specific return value for those arguments. But if you want to call everything a parameter, I'm pretty sure most people are not going to correct you on it. Anyway, kind of getting towards the end here. Variable scope. So variable scope means that when you create a function, any variables you create inside of that function, they only live inside of that function, right? If I have a variable that I call n inside of a function, or even parameter, because parameters are really like variables that are created inside the function, then if I have another function I'm defining, I can actually call that parameter n as well, because this n and this n don't overlap, right? They don't share a scope. It's sort of like anything you create inside the function only lives so long as you're going through that one execution of the function. It doesn't live anywhere else. In fact, if you try to use n in another function that you declared inside of this function, it's going to say that's an undeclared identifier. I don't know what n is because you declared it inside of a function. And so that sort of encapsulates that, all those variables into one place. The reason for that is a little bit technical, but whatever, it's there. Now you can actually create something outside of a function. Variables that are declared outside of a function are considered global variables, and all functions would have access to them. But it's not really great computer science, right? We want to, in general, as much as possible, avoid global scope. For one, it's kind of insecure. I mean, especially if your variable is called x, chances are somebody else is going to do something silly, create an x, and now you've got a problem of, a clashing of variables. In general, C++ will default to using the most local definition for anything. So if I had a function that had an x defined inside of it, or I actually declared x in here, then anything I did with x inside of that function would use the local x rather than the global x. But the fact that I have two variables with the exact same name that are one's global, one's local, now we're getting into confusing territory where people might make a mistake. So in general, global scope is considered a bad thing. Try not to use it. Use local variables as much as possible, variables you declare inside of functions. And then just pass the values back and forth between the functions if needed. You can also overload functions. Kind of the last thing we'll talk about is that a single function can be prototyped and defined multiple times for multiple different types of inputs. So here I have 3 different functions, right? I've got my add defined for 2 integers, for 3 integers, or for 2 doubles, right? So here, when I make the function call, my add, and I send it 3 integers, these all have the exact same name, right? But their parameter types are different. So what it's going to do is it's going to say, okay, so my add with the 3 integers is going to match the center one. So I'm going to go ahead and do the center one. By the way, I don't think the last one can actually receive it or can return a double. So my slide might be slightly off. Return types, I believe, have to be the same in C++ too. But right now, let's just look at the inputs, right? 3 integers, it's going to know to do the center one. Awesome. So it's going to call that one, we're going to get the correct results, and that's great. If I had sent 2 doubles, it would have done the last one. If I had sent 2 integers, it would have done the top one. Now, here's the problem. What if I do this? I'm sending 3 doubles, but I never defined this for 3 doubles. So you'd think what I would do is I'd get an error. And you'd be right to think that, but I mean, you'd be wrong, but like that's the way maybe it should work. But instead, what C++ is going to do is it's going to do what we call an implicit conversion. It says, oh, well, you sent me 3 doubles. I don't have a definition for 3 doubles, so the one that matches the best is actually going to be that center one again. All I'm going to do is I'm just going to truncate the values for all 3 inputs and call the center one, which is going to give me the answer of 11. If you add those 3 numbers together, you do not get 11. I've gotten something far worse than an error. I've gotten a result I did not intend, and it didn't throw an error. So point being, as you're doing this sort of stuff, if you wanted to take 3 doubles, make sure you actually create a version for that. But anyway, you can create multiple different, implementations for different input types and numbers of inputs, and then your C++ will try to pattern match with the function call to see which one to actually execute. That is it for functions this week. You have enough to handle the rest of your week and all your assignments. There will be a secondary video, a supplemental video, talking a little bit more about some of the back-end stuff, just as an advertisement for it right now, because it's optional. I know there's a good chance you won't view it, and maybe you want to get some practice under your belt before you do. But yeah, it's good to know. Basically, there's this concept called recursion that kind of throws people a lot later on. But as we're talking about function calls, if you understand how function calls are actually implemented in hardware with something called the call stack, it makes understanding recursion so much easier. That'll be in a supplemental video. And yeah, until then, if you have any questions, send me a message in Canvas. Have a great week.